Welcome back, everyone. We're going to finish up our discussion of statistics by exploring how to calculate dispersion statistics. Like central tendency statistics, dispersion statistics are used to describe a data set. But why do we need dispersion statistics? Well, sometimes the central tendency measures by themselves are not enough to differentiate between two different samples. For example, look at these two classes here. It's clear from graphs that Class A and Class B study differently. But if we look at the central tendency values, both of these examples have the exact same central tendency statistics. So how do we differentiate between the two? This is where dispersion statistics are more valuable. Unlike central tendency statistics, dispersion statistics focus on the distribution of the scores, not the center value. So they tell us about how the scores are spread out from one another, which allows us to better differentiate between Class A and B from the previous side. There are three methods used to measure dispersion: range, variance, and standard deviation. One of the important things that I've highlighted here on this slide is that all three of the dispersion statistics require interval or ratio level measurements, so you will not be able to do any of these calculations on a categorical variable. The first up is range. This is the easiest dispersion statistic to calculate, but it's also kind of the least helpful. The range is a very simple calculation where you take the highest score and you subtract the lowest score. The bigger the range, the more variance in the data. So if we look back at our classroom study habits graph, we see that the highest value in Class A is 4 and the lowest is 2. So our range is 4 minus 2, which is 2. Class B's highest study hours was 5 and the lowest study hours was 1. So our range is 4. By comparing the range values, we can say that Class B is more dispersed than Class A because the highest and lowest values are more spread out from one another. The problem is that range is like the mean in that it can be affected by outliers. Since range only uses the highest and lowest scores, an extreme value on either end will mess with your data. Here's our IQ table from the previous lecture. Since position 5 is the highest and position 1 is the lowest, I take the IQ score from position 5 and subtract the IQ score from position 1 to get the range of each data set. Like the mean, we see a substantial difference between the ranges of all three columns. Technically, they're all correct, right? Because there is that much spread between the highest and lowest values in each data set. But in reality, we know that all of this is caused by one student's score, so it's not really an accurate look at the distribution for the rest of the student IQ values. The outlier influence on the range is why the dispersion statistics most commonly consulted are variance and standard deviation. These statistics look at every score in the dataset, so they're not as impacted by a single deviant case like the range is. Variance and standard deviation are calculated in a step-by-step process. Variance is calculated first by looking at the deviation of every score. And by deviation, I mean the difference between each individual score and the average score in the dataset. Once you've calculated the variance, then the standard deviation can be attained from the variance itself. Here are the formulas for this. As I've noted on this slide, I will not require you to calculate the variance by hand. However, I do want you to understand how this is calculated. The x minus x bar shown here is the deviance calculation. You take the specific value, the x, and you subtract the average value in the data set. You then square the number to remove any unwanted negatives, and you add all the deviations up. Then you divide by the total number of values in the data set. This gives you your variance. Variance is represented by s squared. Standard deviation is represented by s, which means that it's calculated by taking the square root of s squared. So once you have the variance, you simply take the square root and you get the standard deviation. Realistically, in most cases, the variance is simply a stepping stone that's used to get to the actual statistic of interest, which is the standard deviation. This next part that I'm going to teach you is a simplified version of the standard deviation discussion that you will have learned already in your statistics course. If you need a refresher on this material, I do have some videos on my website, and of course YouTube is always available for more tutorial help. So what we need to know for our research methods interest is that the standard deviation can help us identify where normal data lies in the data set. In a normal curve shown here, approximately 68% of the values will fall within one standard deviation from the mean. 95% of the values will fall within 2 standard deviations of the mean, and 99% of the values will fall within 3 standard deviations from the mean. This means that if we want to find the so-called normal values of data, we can use the mean and the standard deviation to calculate the range of normal values. Again, I'm super simplifying here, but this is the basic principle. So let's go back to our classroom study habit example. We know that the range has already differentiated the two classes, but what about the standard deviation? Now remember, I told you I wasn't going to make you calculate the variance, so I've provided it here for you. The variance of class A is 0.6, and the variance of class B is 2.4. We know that we need to square root these values in order to calculate the standard deviation. So we take the square root of 0.6 and the square root of 2.4, and we get the standard deviation values of 0.78 and 1.55. So now we've differentiated the two classes with all of our dispersion statistics: the range, the variance, and the standard deviation. We can actually make quick interpretations of the distribution based on the standard deviation. The higher the standard deviation is, the more spread out the data will be. That's because we find the spread by adding and subtracting the standard deviation from the mean value. So the bigger that number is, the bigger the spread will be between the subtracted and the added value away from the mean. Now, the last part of the standard deviation that I want to explain is the calculation of outliers. Remember that we've already discussed what an outlier is, but until now we didn't have any set definition for how to tell something is an outlier. You can use the standard deviation to give us a better identification tools to recognize outliers. Simplifying the graph from earlier, outliers are going to fall outside of the 99% range that we discussed previously. The calculation for this is x bar, or the mean, plus or minus 3s, which means 3 times our standard deviation. Doing example is always easier to understand. Here is a classic test, the Wechsler-Bellevue intelligence test. This IQ test is standardized so that the mean value is 100 and the standard deviation is 15. We can use the normal curve properties that we discussed earlier to identify where normal data occurs and what values would be considered irregular or outliers. So let's start by looking at one standard deviation difference. Remember, this range contains 68% of the data set. What we'll need to do is take the formula in two steps. One time through, we'll use the addition option, and the other time through, we'll use the subtraction option. So here's the addition option. We take the mean value of 100, and we add 1 times the standard deviation. So we get 1 times 15, which is 15, and 100 plus 15 gives us 115. Then we do the same thing for the subtraction option, only this time we do 100 minus 15, which gives us 85. This means that 68% of people will score somewhere between 85 and 115 on the Wechsler-Bellevue intelligence scale. We can now do the same thing for the 95% option, which requires us to add and subtract 2 of the standard deviation values from the mean. The mean of 100 plus 2 times the standard deviation of 15 gives us 100 plus 30, which gives us 130. The mean minus 2 times the standard deviation gives us 100 minus 30, or 70. So 95% of people will score between 70 and 130 on the intelligence scale. And lastly, that brings us to the 99% range and the calculation of outliers. Doing the same as before, we take the mean plus 3 times the standard deviation, which equals 100 plus 3 times 15, or 145. Then we do 100 minus 3 times 15, or 55. That gives us a range of 55 to 145. So 99% of the people who take the Wechsler-Bellevue intelligence scale will score between 55 and 145 on the test. What this means is that we know where the normal scores are. So now all we have to do is identify those scores that would not be normal. In this case, anyone who scores below a 55 or above a 145 would be outside the 99%. So they would be the outliers. On a test question, I may give you a hypothetical score and then ask you to determine whether or not the score would be an outlier. All you need to do is the calculations on this slide to figure out the mean plus or minus 3 standard deviations, and then identify whether or not the score fits into that range or whether it's outside of it. Any score not included in the 99% range can be considered an outlier. All right, well, that concludes our discussion of dispersion statistics. Thanks for watching, everyone.